When we started the integration topic, we were looking at areas under a curve, and we started with approximating those areas through different methods until we got to the point where we saw that integration, the process of integration, gives us the area under a curve. In part 9 of this topic, we're looking at areas enclosed by the x-axis, like this area here. And so if we wanted to work out this area, we would simply take the definite integral between the limits a and b of this function of x. And whatever our answer is, that's the area. But what about if we flip this so that the area is below the x-axis? Will it still work as before? Does this integral actually give us the area? Well, let's find out with a few introductory examples. In the first of these two introductory examples, we have to find the area enclosed by the curve y equals 2 plus x minus x squared and the x-axis. So what kind of curve is this? Well, it's a parabola, and because of the negative attached to the x squared, it's a negative parabola. Now, we don't know anything else about where this area is located at the moment, so it's a good idea to sketch what's going on. So we need to get a better idea of this parabola, and so it would be a good idea to factorize it. When we're dealing with negative parabolas, it's usually easiest if we drag the negative completely out the front. Okay, so we're left with the x squared term as positive now, but then we have to adjust the other terms as well, so minus x and minus 2. Now if we just focus on what's inside the brackets, we can factorize it so that we can plot the x-intercepts. So how can we factorize x squared minus x minus 2? Well, factors of negative 2 that add to give negative 1. Positive 1 and negative 2. Remember, if you want to double check, you can always expand. Sort of like when we double check an integration, right? And we do the differentiation just to be sure. Okay, so now that we've expressed our parabola like this, we can graph it. We have x-intercepts at x equals negative 1, right? If we set this first bracket equal to 0, and 2 if we set this second bracket equal to 0. Remember, x-intercepts occur wherever y is equal to 0. Putting these two x-intercepts along with the fact that it's a parabola and the fact that it's a negative parabola, putting all of that together gives us the following graph. And so the area that is enclosed by the curve and the x-axis is in here. And how do we work out this area? Well, we take the definite integral of the function. We now know the limits of our integral are minus 1 and 2. And in integrating our function, what we'll write here is what we saw originally. This will be easier for us to integrate rather than the factorized version. So 2 plus x minus x squared. Starting with the 2, when we integrate, that becomes 2x. The x becomes x squared on 2, and the negative x squared becomes negative x cubed on 3. applying our fundamental theorem of calculus means that we're going to substitute in 2 first of all. So 2 lots of 2 plus 2 squared on 2 minus 2 cubed on 3. And then we are going to subtract what we get when we substitute in -1 for x. And finally here, -1 cubed on 3. Going through the calculation procedure, whether you do it step by step mentally, which is a pretty good idea, or whether you use your calculator, we see that our final answer is 4.5. And because we are actually finding an area, not just the value of an integral, we would state that our area is 4.5 units squared, or square units. Alright, so hopefully that should be more like revision for you. Let's move on to the second of our introductory examples. Find the area bounded by the curve y equals x squared minus 4 and the x-axis. So we're dealing with another parabola again. And in fact, this is just the standard parabola, y equals x squared, moved down 4 spots. If we wanted to factorize it, we can notice that x squared minus 4 is a difference of 2 squares. And so we can write this as x plus 2 multiplied by x minus 2. Or you might just be able to realize straight away that the x-intercepts are going to be positive and -2. So, graphing this, we can see that the area is actually below the x-axis. So let's see what happens when we take the integral. In this case, it's between -2 and 2, and it's the integral of x squared minus 4. X squared becomes x cubed on 3, and the minus 4 becomes minus 4x. Once again, we will apply the fundamental theorem of calculus. So let's substitute in our first value. That's 2. And then we will take away the result when we substitute in our second value. Now, using brackets is especially important when we're substituting in negative values, as it helps reduce mistakes. If you want to calculate this and practice your mental arithmetic, that's absolutely fine. But we'll go straight to the answer, which is -10 and 2/3. How can area be negative? Well, of course area can't be negative. It's always a physical quantity. You either have no area or you have some positive area. But what we've just seen here is that because the area was located underneath or below the x-axis, our integral value was negative. So how do we account for that when we are specifically asked to find an area? So we can't write -10 and 2/3. That's the integral value, but not the area. What we have to do is take the absolute value of our integral. Now I could go right back to the start and put in absolute value signs around the entire integral. That's going to be a bit messy. So instead, let's just say that we've found the integral value, I'll call that I, instead of the area value. And now the area value is simply the absolute value of the integral. So the area is the absolute value of -10 and 2/3. And we know that with absolute values, anything that is negative becomes positive. So to summarise what we've seen in these introductory examples, areas above the x-axis give a positive definite integral, and areas below the x-axis give a negative definite integral. And so when we are trying to find the area below the x-axis, we need to take the absolute value of our integral. Now, it's all well and good if our area happens to be completely above the x-axis or completely below the x-axis, but what about if we've got a mixture of both?